All right, today we are going to be discussing informal code analysis and figuring out how efficient our programs are. So let's talk about algorithms first. Algorithms are a step-by-step process that is going to solve some problem. I believe we've talked a little bit about algorithms during the string whatever lesson. So talking more about algorithms today. And we use algorithms all the time, every day. So let's say I want to make a peanut butter sandwich. Your first step is going to be taking out your bread. Your next step is going to be spreading your jelly on one piece of bread. Your next step is going to be spreading peanut butter on your next piece of bread. You put them together. And apparently, if you like your peanut butter and jelly sandwiches toasted, then you're going to toast it. I don't know why you would toast it after you put your sandwich together. I didn't make these slides, CodeHS did. So let's say you want to read a book. You're going to open your book, and as long as you have pages unread, you're going to read your page, you're going to take notes, and you're going to flip your page. I guess you're only reading textbooks because you're in school, and there's no such thing as reading for pleasure. I don't know. You're always going to take notes on what you read. So what do you guys think is going to make a good algorithm? What qualities should an algorithm have that makes it good? Concise, sure, yeah. Any other guesses as to what would make a good algorithm?
Relatively simplistic.
If it's simple, yeah. All right, so if it's concise and it's simple, it's probably pretty easy to read, right? Easy to understand what's going on. A very big thing is making sure it's correct. Does it do what it's intending to do? And efficiency is also important. Making sure that you're not taking too much time to run your algorithm is a big thing. And both simplicity will definitely add to efficiency. And making it concise makes it much easier to understand. So both of your answers, very good. So algorithms should work as intended. Otherwise, it's not a good algorithm. So does this algorithm do what it's intending to do? Why not?
Because it's only going to print
Nope.
9 times, 10 times. I swear I can do that.
So you're correct. It will not work correctly because we want to loop 100 times, and our loop is only going 10 times. So this program does not solve the problem it was intended to solve. It might work for a different solution, but it doesn't solve the problem we are looking to solve here, thus making it not a good algorithm for this problem specifically. If I were to change my 10 to be 100, that would fix that loop. That would solve that problem. Now, algorithms need to be efficient. And efficiency is important because it's going to affect how fast your program runs and how much processing power your program costs to use. So running any computer program is going to use CPU processing time. Processing time is the amount of time, like I just said, that your computer is spending thinking about and running your program, running all of the instructions you have sent to the CPU. So every CPU, every computer has a limit to how much power it can use at any given time. So let's say this is your box of CPU power, and each application you are running is going to consume some percentage of that CPU power. If you are running too many things, your computer is likely to slow down because you are taking up too much of that CPU power. So it's going to slow down your computer when too much processing is trying to happen all at once. If you have more efficient programs, though, that will take up less processing time, which is going to decrease the amount of CPU that you're using, thus making your programs and your whole computer run faster, which is always good. We can actually monitor how much CPU power is currently being used on your computer. If you have a Mac, you can open the Activity Monitor application. And if you are on Windows, you can open the Task Manager with Control-Shift-Escape, and that will show you all of the currently running processes on your computer, how much CPU power they're taking, how much RAM they're taking. You can see all these different statistics on all of the different things that are running on your computer. So this is really handy for just seeing what's going on inside your computer. Pretty cool. Program speed is also going to affect your program's class. So when you click on some activity on CodeHS or on any website, you're really sending that information over the internet to an Amazon server or whatever server is hosting that website. Servers are really just someone else's computer, essentially. It's an external computer to your own. And then you're going to execute some series of commands on that external computer. So the server is going to run a program that the software engineers at CodeHS have written to save and run your code. And then they will send it to my grading queue to actually grade your code, make sure it all works right. And keep in mind, every computer, especially servers, costs money to run. And the more CPU you're consuming, the more it's going to cost to have the server running. So you want to make sure that you're limiting the amount of CPU you're using in order to reduce costs there. Like I just said. So efficient algorithms make economical use of processing time and computer memory. So there are two big questions we want to ask about an algorithm to figure out how efficient it is. Question one, how long does it take to perform this task? And question two, is there another approach that will get us the answer more quickly? Can I do this in a better way, in a more efficient way? So I'm going to read three algorithms out. You're going to have to tell me which one is the most efficient. So algorithm number one, you declare to a room of people when your birthday is, and you ask if anyone in the room has the same birthday as you. If anyone does, they will say yes. All right, that's algorithm number one. Algorithm number two, your room is full of people still. You ask one of your friends, you tell them your birthday, ask if they have the same birthday. If they say no, you're going to go to someone else, ask if they have the same birthday as you. And you're going to keep repeating until you've looked through every single person in the room or until you find someone with the same birthday as you. Algorithm number three, you are only going to ask questions of one person. They are only going to ask questions of one other person, and so on. You're going to form a chain of people. So you tell Annika, your one friend, your birthday. Ask if she has the same birthday as you. She says no. She's going to have to find out from the next person in the chain. And then you're going to keep going up and down the chain, checking one by one, up and down the chain, if anyone has the same birthday as you. Now, of those three, which was the most efficient algorithm?
Well, since the first one had
One.
Probably one.
So I was a very good reason, since number one had the least amount of words and the least amount of explanation, that's probably the most efficient. That's absolutely correct, because this one takes the least amount of time to execute. You're saying, hey, this is my birthday, does anyone match once? And then everyone in the room has the chance to respond all at once, rather than going one by one through people or going through a huge long chain of people back and forth. That's going to be super duper inefficient. So our goal is to take as little time as possible. Now, it is important to be able to measure, or at least kind of guess, how much computer space and how much time is going to be needed to run an algorithm. And this will let you compare different algorithms to see which one would be better for the problem you're trying to solve. Now, figuring out how much actual time an algorithm is going to take is really, really hard to predict, because there are so many different factors that go into it. You need to keep track of or like different programming languages are going to take different times to run. The computer you're running them on will take different times to run. If there's other programmings or other programs taking up your CPU power at the time, that might make your program take longer to run. If your operating system is new and updated, it might run faster than an older operating system. There's so many different things that go into how long your program will actually take to run that keeping track of that and comparing that isn't really a useful metric. So a more useful metric would be some way that is independent of machines, so we don't have to keep track of specific computers. We can analyze our code itself to see what would be the more efficient algorithm. And we can do this using something called the statement execution count. And this is the number of times that any statement is executed in your program. So any executed statement, let's discuss, there's all kinds of different executed statements. Doing some arithmetic operation, assigning a value to a variable, making a Boolean comparison, doing an input or an output. All of those would count as some individual execution. So if we look at this code, let's look at the number of times a statement is executed. So we're going to read from top to bottom. Our first line, we are doing an assignment. That counts as a single execution. So our execution count is 1. We're going to do another assignment. Also executes once. Our execution count is now 2. Then we're going to enter a loop. We're going to loop from 0 up until n minus 1. It's going to loop n number of times. We're going to perform this single addition. We're going to do this operation, this instruction, n times. So we're going to add n to our execution count. And then after our loop is over, we're going to run this once. We're going to execute that one time. So our total execution count is 3 plus n. We'll execute that many instructions where n is the value we've initialized here. Now, as n gets increasingly large, the constant 3 that we're adding here becomes decreasingly effective in changing our number. So if I have 5 apples, adding 3 is going to add a huge percentage. But if I have 300 apples, adding 3 apples to that pile isn't going to do a whole lot. So usually when we're analyzing algorithms like this, all we are going to care about are those variables. So we're not really going to care about addition or subtraction of any constants because they're not going to change the overall runtime very much. Keep in mind, while you are working with conditionals, this can make figuring out how many statements are going to run a little bit more difficult. With an if and an else, you know that you know that exactly one of those is going to run. But if you just have an if, you have to figure out, is this going to execute my inside statement? Is it not? You have to make sure that you're making that comparison. So tracking can be not super easy every time. If you have a for loop, then when you're incrementing by 1 each time, the execution count is going to be the number you're looping up until minus your initial value. And once again, unless your initial value is pretty close to n, it's not really going to affect a whole lot. So if we plug these into a table, if my initial value is 0 and my n is 10, 10 minus 0, it's going to execute 10 times. If my initial value is 4, my n is 8, 8 minus 4 is going to give me 4. There we go. With nested loops, like we talked about during that last class, we're going to multiply the number of times the outside loop runs by the number of times the inside loop runs. So we're going to multiply n minus our initial value times m minus our initial value here, which is going to give us some math. So if our outside loop goes from 0 to 10, and our inside loop goes from 0 to 5. 10 minus 0 times 5 minus 0, 10 times 5, that gives us 50 times that we're looping through here. Keep in mind, using double for loops is usually going to be less efficient than using single for loops because you're doing multiplication rather than addition, which is always going to increase the number of times you're going to run something. And comparing the number of statements that you're executing is one way that we can figure out which algorithm might be more efficient to solve some problem. And algorithms with a lower execution count almost always are going to be more efficient than their counterparts. So how many times are we going to execute this loop? How many times are we going to execute that print? So n is going to start at 50. And then we're going to divide n by 2. So n is going to be 25, which is greater than 0. So we'll print 25. Then we're going to divide by 2. 12 is greater than 0. 6 is greater than 0. 3 is greater than 0. 1 is greater than 0. And then 0 is not greater than 0. So we're not going to print that. So we are printing 1, 2, 3, 4, 5, 6 times through this loop. All right, between these two algorithms, both of them are going to be finding a character. We're looping over all the indices within a string. We're finding the character at that index. If the character is what we're looking for, we're going to print found. And on the left, when we find it, we're going to break. On the right, we're not going to break. So, of those two, which one is going to be more efficient?
The left one.
The left one, exactly. Because we're going to stop looping as soon as we find that thing we're looking for. So if I'm looking for the letter E, 0, 1, 2, 3, I found it right here. I've executed 4 total things. Where here, I'm going to have to look through every character in my string, even if I do find what I'm looking for. Now, it's possible that these could take the exact same number of statements. In the worst possible case, the letter E is either at the end of the string that I'm looking through, or it's not in there at all. And then in that scenario, those two algorithms would do the exact same thing. They would have the exact same runtime, exact same execution count, because we're going to look through every single element, every single character, no matter what. But in the not worst case scenario, this one will definitely be better because we're going to stop before we get to the end. Does that all make sense? Cool. All right, folks.